The birth of the nuclear atom. At the dawn of the 20th century, atoms were thought to be solid spheres, uniform blobs where positive and negative charges were evenly spread. This view, sometimes playfully likened to a plum pudding or chocolate chip cookie, was championed by J.J. Thomson, the man credited with discovering the electron in 1897. In his model, electrons were tiny, negatively charged dots floating in a sea of positive substance, like chocolate chips suspended in dough. Thomson's contribution earned him a Nobel Prize in Physics in 1906. But even Nobel winners can be wrong about the details. Because lurking in his own lab was a student who would change everything. Ernest Rutherford. While experimenting with how particles behaved around radioactive materials, Rutherford stumbled upon something strange. He and his colleagues, Hans Geiger and Ernest Marston, designed an experiment that would go down in history. The gold foil experiment. They fired a stream of alpha particles, tiny, fast, positively charged bullets, at a thin sheet of gold. According to Thomson's model, the alpha particles should pass straight through. After all, the positive pudding in the atom was too spread out to repel anything. But that's not what happened. While most particles did zip through untouched, a few did the unthinkable. They bounced back. Some even shot off at sharp angles, as if they'd hit something dense and solid. Rutherford was astonished. In his own words, "It was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." From that, Rutherford reached a revolutionary conclusion. Atoms aren't filled with positive goo. In fact, atoms are mostly empty space. At the center lies a tiny, dense, positively charged core. He called it the nucleus. The electrons? They whirl around this nucleus like tiny satellites, scattered far and wide, leaving most of the atom as sheer emptiness. This was the nuclear model of the atom. It destroyed the cookie dough theory for good. But the story didn't end there. Another mind, brilliant and young, took Rutherford's findings and ran with them. His name was Niels Bohr. In 1913, Bohr proposed something radical. Electrons don't just spin randomly. They orbit the nucleus in specific paths, like planets around the sun. Each orbit has a fixed energy level. Electrons can jump to higher or lower levels, but never linger in between. His idea explained mysterious patterns in atomic spectra. Suddenly, science had a way to predict how atoms absorb and release energy. But Bohr's model, too, would be tested. As quantum physics matured, scientists found that electrons weren't always neat little particles. Sometimes they behaved like waves. They didn't travel in defined orbits, but existed as clouds of probability, fuzzy regions where they were likely to be found. Out of this strange behavior emerged the quantum model of the atom, our modern understanding today. Still, it all started with a few rogue particles bouncing off a sheet of gold. And with one scientist bold enough to question the cookie dough. Atomic revival. What do a forgotten scroll, a Victorian lab coat, and a particle accelerator have in common? They each mark a turning point in our ongoing quest to understand the invisible world. A revival of the idea that everything around us, every speck of matter, is built from something unimaginably small. Our story begins not in a lab, but under the bright Aegean sky. It's the 5th century BCE, and a curious philosopher named Democritus walks among the olive trees of ancient Greece. He imagines a strange possibility. What if all matter, stone, water, even his own skin, was made of tiny, indivisible bits? He calls them atomos, uncuttable. To him, these particles are eternal and always moving, surrounded by void. Different substances, he thinks, are made from atoms of different shapes and sizes. It's a bold idea, but not a popular one. Another philosopher, Aristotle, disagrees. He believes all things are composed of 4 elements: earth, air, fire, and water. His theory is simple: poetic, and easier to teach. So for nearly 2,000 years, the atom is pushed aside, lost in the shadows of history. That is, until a quiet man in 19th century England decides to question the old ways. His name is John Dalton, a Quaker, a teacher, and a careful observer of the natural world. In 1808, Dalton notices something strange and consistent. When chemicals react, they always do so in fixed ratios. He concludes that matter must be made of discrete units, atoms, that combine in whole number patterns. Each element has its own kind of atom, with a unique mass and size. He even draws diagrams of these invisible building blocks, little circles with symbols, a visual code for the microscopic world. Dalton's work revives Democritus's idea, but this time it's supported by evidence. And while he receives quiet respect from the scientific community, Dalton lives and dies with modesty, true to his Quaker beliefs. But the story doesn't stop there. In fact, it's just beginning. By the end of the 19th century, scientists begin probing atoms more deeply. In 1897, J.J. Thomson discovers the electron, a tiny negatively charged particle inside the atom. The atom, it turns out, isn't indivisible after all. It has structure. It has parts. With this realization, the atom is reborn again. This time not as a vague idea, but as a complex and dynamic system, waiting to be explored, mapped, and understood. From Democritus's guesses to Dalton's models, from invisible dots to orbiting electrons, the atomic theory continues to evolve, each generation peeling back another layer of the unseen. So what do a philosopher, a teacher, and a physicist have in common? They all believe that truth hides in the smallest things, and they each played a part in reviving the atom, from ancient thought to modern science.